Right guys, I'm a year 12 student and on the side of my A levels I've been doing some further maths. So I finished the complex numbers topic, so I'm going to do some tests and I thought I might as well film them on here. So there's 3 tests on alevelmathsrevision.com. So this is the first one and there'll be 2 to come. So I'll do the tests. If anyone wants to follow along then do so, and then we'll mark it and give ourselves a score and see how we did. So let's get to it. So question 1. The complex numbers of 2 plus 3i and 4 minus i are denoted by z and w respectively. Express each of the following in the form x plus iy, showing clearly how you obtain your answers. So z plus 5w, I'll put it down here. So we've got z being 2 plus 3i, and then we're going to add that to 5 lots of 4 minus I. It's going to be 2 plus 3i plus 20 minus 5i. If we evaluate that, combine the real parts, which can be 22, and then combine the complex parts, so it's going to be minus 2i. That's our answer. 2, okay. So we've got complex conjugates. So this star is meaning a complex conjugate. So the complex conjugate of z is 2 minus 3i. So 2 minus 3i, and we're timesing that by w, which is 4 minus I. So let's put these in brackets. Then we're just going to times each term out, so we're going to get 8. 2 times minus I is minus 2i. Minus 3i times 4 is minus 12i. And then minus 3i times minus I is positive 3i squared. You've got to be careful with this I squared. So let's deal with that first. So we know that I is the square root of minus 1. Square root of minus 1 times square root of minus 1. These square roots are going to cancel, so we're going to be left with minus 1. It's basically going to flip the sign here. So this will become real. This will become minus 3. So we're going to do 8 minus 3, which is going to be 5. And then minus 2 minus 12 is minus 14i. Then 1 over w. So 1 over 4 minus I. So this is another conjugate question. It's almost like rationalizing a complex number. So if you times it by its conjugate, it's going to become real. So if we go for 4 plus I on both sides, then we're going to be left with 4 times 4, which is 16. And then we're going to get minus 4i from here, and then plus 4i from here, so they're going to cancel. We can leave those, and then minus I squared, which is going to be plus 1. Oh, sorry, not I, plus 1. Right, so then times this out, that's just going to be 4 plus I. So we're going to be left with 4 over 17 plus 117i. I'm going to put it like that because it says once in the form x plus iy. That's the first question done. Right, so here's the next question. It says the complex numbers 3 minus 2i and 2 plus I are denoted by z and w respectively. Find, giving your answers in the form x plus iy and showing clearly how you obtain these answers. This is a similar question to last time, it's just manipulating these complex numbers. So let's start with I. So 2 times z, and z was 3, oh not plus, let's get rid of that, minus 2i, minus 3, 2 plus I. Okay, now we're going to times them out, so we're going to get 6 minus 4i minus, and we're minusing, so we'll put it in the bracket, so 6 plus 3i. So that means if we multiply this by minus 1 basically, then we're going to get 6 minus 4i minus 6 minus 3i. And that is equal to 6 minus 6, that's going to cancel. And then minus 4 minus 3 is going to be minus 7i. That's the first one. Yeah, that's right. Okay. So let's go on. Question 2. So we got IZ. Oh, the Z is Z being 3 minus 2i. All of that squared. Deal with the squared in a minute. We'll deal with the inside first, I think. So 3i minus 2i squared. Well, this is still squared, which is equal to 3i, and then this is minus 1, so that's going to be plus 2, and this is squared, so we're gonna have to expand this bracket, so 3i plus 2, I'm going to write it like this, and we get 9i squared, and then plus 6i, and then again plus 6i, and then plus 4. Let's tidy that up. I squared, that's minus 9. Minus 9 plus 4 is minus 5. 6i plus 6i is plus 12i. Yeah. Number 3. We've got z, which is 3 minus 2i, divided by w, which is 2 plus i. So this is another conjugate question, so we want to get rid of this denominator, so we can do 2 minus I. So that's going to make it into a real number. We also have to times this by 2 minus I. Yeah. So let's expand this bottom out. So 2 times 2 will be 4. Then we're going to get minus 2i, and then plus 2i, and then we get minus I squared, which is going to be plus 1. Because I squared is minus 1, do the minus, that's going to turn into a positive. So 3 times 2, that's going to be 6. 3 times minus I is going to be minus 3i. Minus 2 times 2 is minus 4i. And then minus 2i times minus 1i is going to be positive 2i squared. Right, let's keep going with this. So 5 on the bottom. Now this is minus 1, so we're going to get here, we're going to get minus 2 there, so 6 minus 2 is 4. Minus 3i minus 4i is minus 7i. Then we want to write this in this form up here, so 4/5 minus 7/5 I. Let's move on to the next one. Right, so now we're getting into some of the more exam style harder questions. So express 2 plus 3i over 5 minus I in the form x plus ii. So we're still manipulating these numbers. It's not too different, sorry. So 2 plus 3i divided by 5 minus I. Again, we want x plus iy, we want a real denominator. So we're going to times that by the conjugate, so 5 plus I. Then we're going to times this by 5 plus I. Therefore we're going to get 25. And we're going to get over here minus 5i, we're going to get plus 5i, they're going to cancel. Then minus I times I is just plus 1. 2 times 5 is going to be 10. 2 times I is going to be plus 2i. 3 times 5 is going to be plus 15i. and then 3i times I is plus 3i squared. So we're going to have 26 on the bottom divided by 10, and this is minus 1, so this is going to turn to be minus 3. So 10 minus 3 is 7. 2 plus 15 is going to be plus 17i. Right, so then we're going to get 7 over 26 plus 17 over 26i. That should be that one, I think. Right, the complex numbers z and w are given by these two numbers. Just saying, these are quite similar because this is the first test which is on the basics of them, mostly timesing them out and manipulating them. So we're just going to do this, and then next we'll move on to the harder stuff in the topic. So, alright, 3z, which is 4 plus 3i, minus 4 times 6 minus I. That's equal to 12 plus 9i minus 24 minus 4i. Now, we want to times by the minus 1, so 12 plus 9i minus 24 plus 4i. That's going to give us 12 minus 24 is minus 12, and then plus 13i. That should be the answer. And number 2 is, sorry, I cut that off, but that should be it. That should be a W there. So we're saying that means the conjugate. So the conjugate of z is 4 minus 3i divided by w, which is 6 minus I. Again, we do the conjugate of this, so 6 plus I. 6 plus I. Come out with 36. The 2, 6i and minus 6i cancelled. And then we're going to get minus I squared, which is plus 1. 6 times 4 is 24. 4 times I is plus 4i. Minus 3 times 6, minus 18i. And then minus 3i times I is minus 3i squared. That's so 37 on the bottom, divided by 3i squared. This is minus 1, so it's going to turn into 3. So 24 plus 3 is going to be 27. Plus 4i minus 18i is going to be minus 14i. Can we simplify? I don't think so. Might be wrong, but I don't think so. So 27 over 37 minus 14 over 37i. Right. Right. Here we get some harder ones. See that? 7 marker. That's when you know. So 1 root of the quadratic equation, which is this, where a and b are real, is 16 minus 30i. So I'm thinking that if a and b are real and we've got a complex root, so this is a complex root, then the only way for the coefficients to be real is by having the other root as the conjugate. So I think that's what this principle is working off. So I'm going to say I, write down the other root. So I'll just, the other root is going to be 16 plus 30i. Because then when you times those together, they're going to make real roots. Sorry, real coefficients. So that's done. Find the values of a and b. Right. So we know that these are our roots, but we want to find the brackets that make these roots, basically. So the two brackets could be x, and then we've got to have minus 16 minus 30i. That's going to make this, because then x, to make this bracket 0, you would need x to be 16 and then 30i. That's going to make 0. And that's going to be times by, if we look at this root up here, then that's going to be x, again minus 16, but then plus 30i. So that's our two brackets. Now it's just a case of a lot of expansion. So we've got x squared, of course, minus 16x plus 30ix. And then we go for the minus 16, so minus 16x, minus 16 times minus 16, I do not know off the top of my head, let's put it in the calculator. 16 times 16 is 256. I feel like I should have known that. So we've done minus 16 times minus 16, now minus 16 times 30 is going to be minus, so it's 16 times 30, 480, minus 480i. Now we times by the 30i, so this is going to be minus 30ix. And then positive, what is it, 480i. That's what our 30 times 16 before was. And then minus 30 times 30i is going to be minus 900i squared. Right, so we've got this long equation, but some things cancel. So this cancels with this, plus 30 minus 30. This cancels with this, and I think that's it. So we also know that this is actually going to be a real number, so it's going to get rid of the I, because I squared is minus 1, so we can do this is going to be 900, because minus 900 times minus 1 is 900. So we're going to get x squared, and then we can join these terms up, so minus 32x, and then 256 plus 900, which is positive 1156 on the calculator. So we've got this equals 0. So if we're trying to find a and b, then a is going to be minus 32, and b is going to be 1156. You can see that they're both real because we use those conjugates. This 7 marker I'm going to do on the next sheet of paper, so I have a bit of room. Right guys, so we move on to question 3. So it says use an algebraic method to solve the quartic equation y to the 4 plus ay squared plus b. And we have these coefficients we found before. I'm thinking that, does this equation have some sort of relationship here? So it's like x is equal to y squared. x is equal to y squared, because if you sub that in, you get the other equation. It's a difficult one. I don't know if that I can really do anything with this. I'm thinking of another way to do it. Yeah, I'm not sure. I'm gonna have to go and look at the mark scheme for that one at the end. If any of you got that one, then put it down in the comments how you did it. But no, that stumped me. Alright, well. Right, let's see if we can do this one then after that tough last one. So, the complex number of 3 plus ai, so we've got an unknown in a, where a is real, is denoted by z. Given that arg z is equal to 1/6 pi, find the value of a. Then we'll work with that a bit later. So the first bit, I'm thinking we've got arg, so let's draw a Argand diagram. So let's say if we go 3 across, and let's just say a is here. Right, so we're going to draw this triangle. We're going to call this a, and we're going to call this 3, because this is our real axis and this is our imaginary axis. So we can say that the arg is this angle here. So if we're trying to find arg z, it's going to be theta. So if we know that this is a right angle, so you can say that tan theta is equal to opposite, which is going to be our a, over our adjacent, which is 3. We also know what theta is, so we can sub that in. So we can say that tan of 1/6 pi is equal to a over 3. So if we times tan of 1/6, so tan of 1/6, 1/6 pi, sorry, and we times that by 3, then we're going to get a. Actually, hold on. Sorry, I need to get my other calculator, which is in radians. It's got to be in radians. So sorry, tan to the just tan of 1/6 pi times by 3. Oh, so gives us as a being √3. So that means it'd be 3 plus √3i. Right. And then it says, and hence, so we're going to be using this somehow, find modulus of z and the conjugate of z minus 3. So let's start with the modulus. The modulus we can use our Argand diagram. So we know that modulus is this side. Should we call it the modulus of z? Is this side here. So how are we going to find that? We can do Pythagoras. So a squared. Actually, we don't need to say a squared because we know what a is. So we can say that √3 squared plus plus 3 squared, yeah, equal is all square rooted is going to be our answer. So the square root of √3 squared plus 3 squared gives us 2√3. That's equal to the modulus of z. That's that. And then hence find the conjugate of z minus 3. So the conjugate of z, we know that we'll write z is equal to 3 plus root 3i. So therefore the modulus, no, sorry, not the modulus, the conjugate is going to equal 3 minus root 3i. So then if we do 3 minus root 3i, and then we minus 3 from it, then we're just going to get minus root 3i. So these are our answers. And we'll move on to the next one. Right, here's the last one. Let's see if we can do this. So question 7. The complex number x plus iy is denoted by z. Express this equation in terms of x and y. So we sub x plus iy in for z. So we can say that 3 times by x plus iy times by the conjugate of z, which is going to be x minus iy, minus the modulus of z squared. So let's just do our working up here. So if I draw an Argand diagram and we have a point here, this is our modulus. And to find the modulus, we do Pythagoras on sides A and B. So our A and B are actually x and y, because this is our imaginary axis and this is our real axis. So we can say that the modulus of z is equal to the square root of x squared plus y squared. However, we don't want just the modulus, we want the modulus squared, so therefore the modulus squared is equal to x squared plus y squared. So minus x squared plus y squared. Right, so let's times these brackets out. So 3x squared minus, let's go xyi, plus xyi, and then minus y squared I squared minus x squared plus y squared. So these cancel, and y minus y squared times I squared, so I squared is minus 1, so therefore that's going to equal positive y squared. So we're going to do, let's just rewrite out here, 3x squared plus y squared minus x squared plus y squared. Put those in brackets. So, well, we don't actually have to times this out because we can see that we have 3 lots of x squared, y squared, and then here we're minusing 1 lot, so therefore we're going to get 2 lots of x squared plus y squared. And if we want to expand that out, we can say 2x squared plus 2y squared is equal to 3z times the conjugate of z minus modulus of z squared. Right, so now that I've finished the questions, I'm going to mark it myself. I won't record it, and then I'll tell you where I went wrong and then give myself a score. Right guys, so I just finished marking my test and I got all of them right except this question that I'm on right now. So I've had a look at the mark scheme and I still don't fully understand it. So it's talking about equating real and imaginary parts. Then you're going to get these two quadratics that are going to solve. I'm not quite sure how this part works, so if any of you in the comments know how to do this and have done it and could put an explanation in the comments below, then that would be great. I'd be interested to know that. But it's quite strange, this part up here. I've never seen that before. So overall I got 42 out of, it would have been 49, times that by 100, which is, let's see, it's about 85%, which I'm pretty happy with for a bit of self-taught further maths. So next time I'm going to do the other section, which is on Argand diagrams and loci, and that's going to be from the Edexcel Pearson textbook, and I'll pick some exam questions out of that, and then I'll post them on here as well. So thanks, guys.